Okay, so we have here a sample problem for chapter 14. Chapter 14, still it is about titration. But this time we are going to study on the titration curve. Now, so in this problem, we are going to compute for the pH of the analyte, or that is the one found in the class, and we are going to draw or sketch the titration curve. Now, the titration curve, it is a diagram between pH versus the volume of the titrant. So, the pH there, that is the pH of the analyte or the pH of the solution found in the flask. Okay? So, we have here the problem for 14.2. We are going to calculate the pH during the titration of 50 ml of 0.05 molar sodium hydroxide. So, sodium hydroxide with a concentration of 0.05, it is our analyte, so that is the one placed in the flask. Okay? So, the amount of the analyte is 50 ml. So, you have here, excuse akong drawing. So, 50 ml of sodium hydroxide with a concentration of 0.05. Now, this substance or the analyte will be titrated with 0.1 molar hydrochloric acid, of course, at 25 degrees Celsius. Now, we are going to determine the pH when the solution, sodium hydroxide, will be titrated with 24.5 ml of 0.1 hydrochloric acid. So, hydrochloric acid is our titrant. Then we are going to compute the pH, determine also the pH once it is titrated with 25 ml. Take note of the difference of the volume, it's only 0.5, and the pH at 25.5. Now, in this problem, we have to determine also whether at what volume wherein our system is at before equivalence point, at equivalence point, and after equivalence point. So, by definition again, so when we say equivalence point, that is the point wherein, if it is a titration between acid and base, it is a point wherein there is complete reaction between the acid and the base, or it is completely neutralized. Okay, so if it is a titration of a strong acid with a strong base, so we know already in theory that the pH at equivalence point is equal to 7. That is, if it is a strong base and a strong acid. So in this example, we have sodium hydroxide, which is a strong base that is titrated with hydrochloric acid, which is also a strong acid. So theoretically, we know already that the pH at equivalence point is 7. But we are going to determine which one or what volume does the 50 ml sodium hydroxide will be neutralized completely by the hydrochloric acid, that is at equivalence point. Then the other is after equivalence point. So again, there are 3 steps that you are going to consider. Before equivalence point, at equivalence point, and after equivalence point. But before that one, we have to determine first initially, meaning initially, so there is no volume of the titrant yet added into our analyte. So initially, that is, we will have here a volume is equal to 0 ml of hydrochloric acid, meaning you have not added yet a hydrochloric acid into our analyte. So the purpose there is we have to determine what is the pH of the analyte, and at the same time, what is the amount of the analyte in terms of millimole or moles. Now, since we have ml here as volume, so we will compute the amount of the reactant, hydrochloric acid or sodium hydroxide in terms of millimole. Since we have the volume and the concentration of sodium hydroxide, we would be able to determine the millimole of sodium hydroxide. The amount in terms of mole. So we have here 0.05, that is molar, so we can have it in millimole over ml times the amount of the analyte, which is 50 ml. So by computation, this will be equal to 2.5 millimole of sodium hydroxide. So meaning, initially, no hydrochloric acid yet is added into the analyte, so the amount of the sodium hydroxide in terms of millimole is 2.5. Now, if you are going to determine the pH, initially the pH of sodium hydroxide, since this is a strong base, so once it will ionize, it is completely ionized. So whatever is the concentration of sodium hydroxide, that will be also equal to the concentration of the hydroxyl ion. So since it is a base, so what we can compute is the pOH, which is equal to the negative log of the concentration of the hydroxyl ion. Again, since it is a strong base, so it will be completely ionized into sodium ion and hydroxyl ion. So therefore, whatever is the concentration of the sodium hydroxide, that is also equal to the concentration of the hydroxyl ion. So this will be equal to the negative log of concentration of sodium hydroxide is 0.05. So if you are going to compute this one, this is equal to negative log of 0.05. That is 1.30. That is pOH. So since we have to determine the pH, so therefore pH will be equal to 14 minus 1.3. And that is equal to 12.7. Okay. So the pH of the analyte before originally before hydrochloric acid is being added into it, that's 12.7. That's the pH. That is at initial condition. So if you are going to add now, if you are going to titrate this one with hydrochloric acid, we are going to add how many ml? 24.5 ml of 0.1 molar hydrochloric acid. Okay, so with this amount, so how many millimole of hydrochloric acid? So at 24.5 ml of 0.1 molar hydrochloric acid. So the amount of hydrochloric acid here is in millimoles will be equal to, so millimole of hydrochloric acid will be equal to 0.1. This is millimole per ml. The volume is 24.5 ml. So this is equal to 0.1 times 24.5. So that is 2.45 ml of hydrochloric acid. Okay. Now once this amount, this is millimole. This is millimole of hydrochloric acid. So once this amount of hydrochloric acid is added into our 2.5 millimole of sodium hydroxide, so there will be some amount of sodium hydroxide that will be consumed because it will react with 2.45 millimole of hydrochloric acid. Now the question is, how many millimoles of sodium hydroxide reacted with 2.45 millimole of hydrochloric acid? So again, we are going to use stoichiometry. So you can have the reaction of you can have the reaction of hydrochloric acid, and I will just write it here, the reaction. So it is a reaction between sodium hydroxide and hydrochloric acid, so that we would be able to get the relationship between hydrochloric acid and sodium hydroxide. So we have sodium chloride and water. Okay, so that's the equation is already balanced. So the relationship between sodium hydroxide and hydrochloric acid is 1:1. So if there will be 2.45 millimole of hydrochloric acid, so it will react with how many moles of sodium hydroxide? That is also 2.45. So if we are going to compute for this portion only, and the rest delete na because it's only 1:1. So if we are going to compute the amount of, you can have millimole of sodium hydroxide reacted or consumed, so that will be equal to, so reacted or consumed. So if you have here 2.45 millimole of hydrochloric acid times the stoichiometric relationship, that will be 1 millimole of sodium hydroxide for every 1 millimole of hydrochloric acid. So you can cancel it out. So the amount consumed is, or reacted, is 2.45 millimole of sodium hydroxide. So meaning, if you have 2.5 initially millimole of hydrochloric sodium hydroxide, and some amount of this one reacts with 2.45 millimole of hydrochloric acid. So what is the amount? 2.45. So therefore, if you have 2.5 millimole of sodium hydroxide, and the ones that is being consumed to react with this amount of hydrochloric acid, 2.45, so there is still sodium hydroxide that remains in the flask. So what is in excess after adding 24.5 ml of 0.1 molar hydrochloric acid? What is in excess in the flask is still sodium hydroxide. How much is the excess? So you can compute. So if you have 2.5 minus 2.45, so how much is the excess? So that is, you just get the
0.4.
Excess sodium hydroxide since there is excess, so meaning it is not still at equivalence point. So this portion here, this is before equivalence point. So why it is before equivalence point? Because not all of the exactly the same amount of sodium hydroxide is reacted with hydrochloric acid. So there is still a small amount of sodium hydroxide that remains in the flask after the addition of 24.5 ml of hydrochloric acid. So what is in excess after this addition is still sodium hydroxide. Because originally we have 2.5 millimole of sodium hydroxide minus the one that is being consumed, that is used to react with 2.45 millimole of hydrochloric acid. So the amount of sodium hydroxide reacted is 2.45. So you have 2.45 millimole of sodium hydroxide. This is the one reacted. So what is the amount that remains or in excess? So you have 2.5 minus 2.45, that is 0.05. Not 0.02. So 0.05 millimole of sodium hydroxide. This is the one now found in the, this is the amount found in the flask. Okay, it's no longer 2.5 millimole sodium hydroxide, but 0.05 millimole of sodium hydroxide. Now, since we are going to compute for the pH, so take note na, the pH that we are going to compute is the pH of the solution that is in the flask. So, at this time, once you have added this value, what is the substance that is found inside the flask is 0.05 millimole sodium hydroxide. So we have to get the concentration. So the molarity of the solution is the number of moles, 0.05 millimole. Divide this one by the, okay, I'll just write the word. So determine the concentration. Okay, so the concentration will be in molarity, moles per millimoles per ml. So that is, it is sodium hydroxide still that is present in the flask, which is 0.05 millimole divided by the total volume of the solution inside the flask. So the total volume now will be 50 plus 24.5. That is the total volume. So you have 50 initially, then it is titrated with 24.5 ml. Okay, just write the units. So you have initially you have 50 ml, then it is titrated and added with 24.5 ml. So therefore, the concentration now of the solution in the flask is 0.05 divided by 74.5. That is 6.7114 times 10 to the negative 4 molar. Okay? Now, since, again, this is a base, sodium hydroxide, it is a strong base, so it will ionize completely. So, therefore, you can compute immediately, since it is a base, so compute for the pOH. Negative log of the concentration of the hydroxyl ion. What is now the concentration of the hydroxyl ion? That is equal to the concentration of the sodium hydroxide, which is 6.11. So you have negative log of 6.114 times 10 to the negative 4. And that is pOH is equal to the negative log of 6.711. 6.7114 exponent negative 4. That's 3.17. So the pOH, the pH then is equal to 40 minus 3.17, which is equal to 10.83. Okay? So, upon the addition of 24.5 ml of hydrochloric acid, the pH now of the solution inside the flask is 10. This is now the pH, 10.83. Before the addition of 24.5, so meaning initially, the pH is 12.7. So once hydrochloric is added, the pH reduces to 10.83. Okay. Now, what will be the pH if 25 ml will be added? So, before it's added with 24.5, so there will be additional of 0.5 ml of HCl. So, it becomes 25. So, if this is already 25 ml, there will be addition of 25 ml of hydrochloric acid. So, what is now the amount? So, if you have 25 ml of 0.1 at 25 ml of 0.1 molar hydrochloric acid. So, what is the amount here in millimole? So, that is 0.1 millimole per ml times 25 ml. So, the millimole is, of course, 2.5. 0.1 times 25, of course, that is 2.5 millimole of HCl. What have you noticed? If you have 2.5 millimole of HCl, since the stoichiometric relationship between sodium hydroxide and hydrochloric acid is 1:1, so it will react how many millimole of sodium hydroxide? So that is also 2.5 millimole of sodium hydroxide reacted with 2.5 millimole of hydrochloric acid. So same with this one. So you can have millimole of sodium hydroxide reacted for 2.5 millimole of hydrochloric acid. So since the ratio is 1:1, so you have here 1 mole of sodium hydroxide for every 1 millimole of HCl. So you can cancel it out. So it is also 2.5 millimole of sodium hydroxide. Okay? So initially, before the addition of hydrochloric acid, the amount of sodium hydroxide inside the flask is 2.5. So the ones that is reacted, if you have 25 ml of hydrochloric acid, is 2.5 millimole of sodium hydroxide. So therefore, there will be no more sodium hydroxide. So what remains at 25 ml of 0.1 molar hydrochloric acid? So at this point, there will be no more sodium hydroxide. So meaning, all of the 2.5 millimole of sodium hydroxide, all are being consumed or reacted with 25 ml of 0.1 molar. It's 0. So, sodium hydroxide remaining, there will be no more exist. So, I'll just write it here. Sodium hydroxide that remain will be equal to 0. So, initially, that's 2.5 millimole of sodium hydroxide minus the ones that reacted, which is 2.5 millimole of sodium hydroxide. So that is equal to 0. What is the meaning now? Now, since all of the amount of sodium hydroxide is completely consumed, exactly the same. No exist of sodium hydroxide, no exist of hydrochloric acid. So meaning, this is now the equivalence point. So this is now an equivalence point. So meaning, when we say equivalence point, that is the point wherein all of the sodium hydroxide in the flask has been completely neutralized by the hydrochloric acid. So therefore, if we have 50 ml of 0.05 molar of sodium hydroxide, this will be completely neutralized by the addition of 25 ml of 0.1 molar hydrochloric acid. So meaning all of the sodium hydroxide has been reacted. So meaning if that is being reacted, what will happen now with the solution? No sodium hydroxide, no hydrochloric acid. So meaning you're going to compute for the pH of the solution inside the flask. It will be based on the ionization of water. This one. So in our chapter 12, I think, that was chapter 12, the ionization of water. So it will be based completely on the ionization of water. So I'll just write it here. pH will be based on the ionization of water. So what was the ionization of water? We have, do I have to write the equation again? Ayan, for review also. So you have hydronium ion and OH ion. Okay, you have 2 moles of water here. So you will have the Kw of water will be the concentration of the hydronium ion times the concentration of hydroxyl ion. So meaning here the ionization constant of water is 1.01 times 10 to the negative 14. If we do not know the concentration of hydronium ion and OH ion, so we leave this one as X. So this one, the concentration of hydronium ion and OH ion are the same. So solving for the value of X, so this will be square root of 1.01 times 10 to the negative 14. So X then here is 1.00 times 10 to the negative 7 molar, which is equal to the concentration of hydronium ion, which is also the same with the concentration of the OH ion. I have no more space. What will I do? I'm going to clean the board, or this one. So this is actually the titration curve for this problem. So maybe I'll just redraw this one. So I'll just erase this one. So I'll just redraw for the titration curve. Okay, so the concentration now of the hydronium ion is equal to the concentration of hydroxyl ion, which is 1 times 10 to the negative 7. So if you're going to get the pH, so pH then would be equal to the negative log of the concentration of the hydronium ion, which is equal to the negative log of 1 times 10 to the negative 7, which is equal to 7. Okay? So this is at equivalence point, the pH of the solution inside the flask is equal to 7. That is titration of a strong base with a strong acid. Okay, that is at equivalence point. Okay? At equivalence point, before equivalence point. Okay. Now, since at equivalence point, it needs 25 ml of 0.1 molar hydrochloric acid. So, if the addition of titration of hydrochloric acid into the sodium hydroxide continues, like addition of 25.5 ml, so it is already beyond. It is already beyond equivalence point. Okay, beyond equivalence point. So this is now the point that is after equivalence point. So after equivalence point, what is in exist? Since no more sodium hydroxide all has been reacted with hydrochloric acid, So after equivalence point, what is in exist is the hydrochloric acid. So what is the amount of hydrochloric acid if you have 25.5 ml of 25.5 ml of 0.1 molar hydrochloric acid. So the millimole of hydrochloric acid here will be equal to, of course, 0.1. This is millimole divided per ml. Multiply it with the volume, which is 25.5 ml. So this is equal to 2.55. So 25.5 times 0.1, so that is 2.55 millimole of hydrochloric acid. Okay? Now, since there is 2.5 millimole of sodium hydroxide initially, and all of this has been consumed at 25 ml of 0.1 hydrochloric acid. So at this point, what is in exist is hydrochloric acid. So the exist now here is hydrochloric acid. How much? That is 2.55 millimole minus the one that has been reacted, which is 2.5. So what is, because the 2.5 millimole of hydrochloric acid here has been reacted with 25 ml, 50 ml of sodium hydroxide, or 2.5 millimole of sodium hydroxide. So minus 2.5 millimole, so that is equal to 0.05 millimole of HCl. So this is the amount of hydrochloric acid that has been in exist in the solution. Because again, the 2.5 here, this one, the 2.5 millimole of hydrochloric acid, this is completely consumed by reacting with the 25 with this one, with the 2.5 millimole of sodium hydroxide. So this is the amount in exist. So what is now the concentration? So the concentration of HCl in molarity will be equal to the amount in millimole, 0.05 millimole, divided by the total volume of the solution. So what is now the total volume? Initially, we have 50 ml plus the addition of how many ml hydrochloric acid? 25.5 ml. So the total volume is 75.5. So the concentration now of the exist hydrochloric acid is 0.05 divided by 75.5, and that is 6.6225 times 10 to the negative 4. This is molarity of HCl. Okay. Since this is an acid, hydrochloric acid, so it's a strong electrolyte, it will be completely ionized into hydrogen ion and chlorine ion. So therefore, the concentration of the hydrogen ion is just equal to the concentration of the hydrochloric acid. So therefore, pH is equal to the negative log of 6.6225 times 10 to the negative 4. So the pH of the solution is negative log of 6.6225. Exponent negative 4 is 3.18. 3.18, or approximately 3.2. Okay? So, we have now the pH of the solution. So we are ready to sketch the graph of the titration curve, the one that I draw here, and it has been erased. So I'm going to redraw it again. Okay, so we will just have the summary first. If you have, because the titration curve, it is the graph of the pH of the solution in the glass versus the volume of the titrant. So if we have the volume here, volume of the titrant, which is, what is our titrant? Hydrochloric acid, versus the pH of the solution that is in the flask or the analyte. So if you have a volume initially 0 ml, so you have not added sodium hydroxide, the pH is 12.7. If you added 24.5 ml of hydrochloric acid, the pH is 10.83. 10.83. If we added 25 ml, the pH is 7. If we added 25.5 ml of hydrochloric acid, the pH is 3.2. We will just round it off to 1 decimal place. So this one is 10.8. So we can make now the graph of the pH versus the volume of the titrant. So I'm going to draw where? There. So here again, draw again. So this is now the sketch of the titration curve. I hope I can draw it very well. Straight and straight. So this is now the titration curve. So we have the okay. I have assistant here. What is it? And pH here. Volume here. Oh. pH. Ay, nako. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3. Okay, so we're going to make the graph. So at zero volume of the titrant, so we have added nothing. The pH is 12.7, so approximately it's here. So it is point that's 12.7. And if we added 24.5 here, the pH is 10.3, about 10.3. So possibly it's here. I'm going to use a ruler so that it will be straight. Buklatan nyo eh. So sweet. Slide. Gusto na. There we go. Parang the dots, and if it is 25 ml, the pH is 7. So maybe I'll just have it here, dot, and 25. Lang, para madali ta. Okay, 25. And at 25.5, the pH is 3.2. So somewhere here. Again. So it's around here. So somewhere over the ring. Then you can connect all the dots. Take note of the form of the graph for the titration curve. So this must be drawn like this. Oops. It must be like this. Excuse for my drawing. Basta it's going to be somewhere here. It's around like this. And going there. And it will be asymptote. Okay? So actually the somewhere in this portion, it will be somewhat straight here. Excuse for my drawing. It's not accurate. But more or less, this is the diagram of the titration curve. So this is at equivalence point, this portion, at pH equal to 7, this is the equivalence point. Okay? Here, at top, before the equivalence point, here, this is after the equivalence point. So you have an assignment actually for this chapter 14. You're going to do it like this, I think, but you have 10 coordinates. This is only, how many coordinates? 1, 2, 3, 4 coordinates only. Your assignment is around, I think, 10 coordinates. So this is the problem on the titration of a strong acid and a strong base, or strong base with a strong acid. And the titration curve. The pH is equal to 7.